All right, so last week we finished up talking about ring opening of epoxides, and we said you can make an epoxide really easily using MCPBA or peroxyacetic acid, and it really depends on whether or not the ring opening is occurring under acidic conditions or basic conditions, right? If it's occurring under acidic conditions and you've got a tertiary carbon, your nucleophile is going to attack the tertiary carbon. If it's done under basic conditions, your nucleophile is always going to go after your less substituted side. And then we had this weird exception in the middle where we said if it's under acidic conditions and you don't have a tertiary position, then it will go after your less substituted side. So the easiest thing to remember is anytime you've got acid in a tertiary carbon, remember that your nucleophile will attack there. Any other time, it's going to go after the less substituted side. Okay, so let's make a little reaction map. And by little, I mean big. And I like to split this into two halves, and we'll do under non-acidic conditions up top. And then we'll add our acidic conditions down below when we're done. So let's draw in a standard epoxide in the center. We've got a bunch of different reactions that can occur under non-acidic conditions. One would be to throw in something like a thiol. And we'll quench this with H2O. Why do I need to quench it with water at the end?
Why don't you just add a S minus?
That and, well, actually the sulfur in this case has a negative charge. It's going to attack the backside of this carbon and slingshot this open, right? So that oxygen ends up with a negative charge. We have to protonate it at the end. So these are under non-acidic conditions, which means it's always going to go after the less substituted carbon. So when we do this, we always have to quench with water to ensure that we're getting our neutral organic product. And in this case, we're going to form a new thiol out of it. Does that make sense? So that's one reaction we can do. We can also do the same reaction with cyanide. However, just like before, we need to treat this with water. And this is a nice way for forming nitriles. A nitrile is really just something with the cyano group coming off of it. You can do this same reaction using an alkoxide. So we could do something like sodium methoxide followed by water. And this would allow you to make an ether from an ether. So any alkoxide works. However, the more sterically bulked up they are, the slower the reaction is going to be, right? So in this case, methoxide is a really nice nucleophile because it's not super bulky. If you have terbutoxide, the reaction is going to be really slow and sluggish. The next one that's kind of cool is you can treat this with a Grignard reagent. And you can actually add in a new carbon group to the less substituted side. So you can imagine if you want to extend your carbon chain, you can actually treat an epoxide with the Grignard reagent and tack on some sort of new R group off the end. And then the last one that's also pretty cool is you can treat this with lithium aluminum hydride followed by water. And what do you think the nucleophile is going to be for lithium aluminum hydride? Yeah, just hydride, H minus. So you can ring open an epoxide with hydride. However, it's not usually that synthetically useful because we know a ton of ways of making alcohols in various ways, shapes, and forms, right? But it is a possibility if you want to do ring opening of an epoxide. Okay, so let's kind of cut this in half. Everything above the green line will be under non-basic conditions, and then we'll do, or under basic conditions, and then we'll do acidic conditions down below. So we've seen some of these before. The first one we saw all the way back in chapter 9 was what happens if we treat this with dilute acid. Then we can get our anti-diol. So the alcohol that was added in is now coming off of this more substituted side of your alkoxide. The next one we can do is we can treat this with catalytic acid and some sort of thiol. And if you do this, again, you're going to attack the more substituted side as long as it's tertiary. And you can actually get your thiol attached in a different fashion. You can do this with regular alcohols too, instead of a thiol. And in all of these, it's important to remember that you're getting essentially anti-addition, and you have to invert the stereocenter where your nucleophile attacked in. The last one that's kind of nice is if you just treat this with a halo acid, so something like HCl or HBr, you can first protonate it, and then your conjugate base, that halide with the negative charge, can actually be a weak nucleophile and do a ring opening. And this will allow you to make a new halogenated compound. So all of these are under acidic conditions. That's why I was telling you guys that epoxides are really powerful intermediates, because you can branch them out in a ton of different directions. And then later on this year, we'll actually discuss a bunch of ways of transforming things like nitriles into a bunch of other functional groups. So this is a really unique way of derivatizing your product. So let's do some practice problems. And I'll give you guys a minute to work on these as a team, but try to show the full mechanism. Oh.
And these are still acidic.
I'll give you guys different situations. Okay, so let's do this one, and we're going to treat it with MCPBA, followed by, actually, sorry, I'm going to add in another methyl group, catalytic acid, and methanol. So you don't have to show the mechanism for the MCPBA part, but show the mechanism for step 2. And then once you think you got it, check with your neighbor. You guys are very quiet today. You don't have to whisper. You guys can talk about it.
It's me.
I'll show you guys a good shorthand too to make your life a little bit easier. Let's abbreviate this pH.
It doesn't matter if it's capitalized one way or the other.
I mean pH with a capital P?
I mean, I capitalized both the P and the H. That's fine.
Technically it's supposed to be capital P lowercase h.
Otherwise, you have the negative log.
All right, give me a thumbs up if you feel comfortable with the epoxide intermediate. A few thumbs. All right, let's take a look at this. And just like before, we said that when you form an epoxide, you have to pay attention to the stereochemistry, right? So in this case, if we look at these methyl groups coming off the alkene, they're coming off the same face, which means they need to be coming off the same face of your epoxide, right? So you could have them as dashes or wedges, however, they need to be consistent. And the phenyl group in this case would be a wedge if that methyl group is a dash. So we'd have this. Is that the only product we would get out? Nope, we'd also have the enantiomer, right? So I'll just write plus En for the sake of argument. All right, step 2, we're going to treat this with our acid. What sort of catalytic acid would we be likely to use?
Sulfuric or phosphoric.
Yeah, sulfuric or phosphoric acid. You really don't want to choose an acid where the conjugate base could be a good nucleophile, right? Otherwise, it's going to ring up in your epoxide. Sulfuric acid's really good for this. So we can protonate it. That gives us our next intermediate. And it's important to remember that you would protonate your enantiomer too. All right, and now we've got methanol floating around.
Make sure you label as a phenyl.
Oh, thank you. My pen's battery is sometimes unresponsive. So which carbon do you think the methanol is going to attack?
Tertiary.
Yeah, the tertiary position. Because we're under acidic conditions, the rules flip. And our methanol is going to favor attack at our tertiary position. We're going to slingshot this open. We now have our protonated methanol underneath. All right. The methyl group on the right would remain a dash because that carbon's been untouched. What about the methyl group on the other carbon? Should it be a dash or a wedge? Specifically, I'm referring to this methyl group. What happens when the backside attack occurs? Yeah, it's going to flip inside out like an umbrella, right? In this case, the way I have it drawn, it's still going to remain a dash, but it's going to be pointed in the upward direction, right? So stereochemistry has been inverted, but you have to be careful with how you draw it. So this would be our penultimate product. Last but not least, we would deprotonate, and we would get to our final ether product where we've got our methoxy group attached. So there are two things you got to remember anytime you're doing ring opening of epoxides. The first is regiochemistry, which carbon is your nucleophile going to attack? And then the second is stereochemistry. You have to remember to invert your stereocenter because it is an SN2 style reaction. Does that make sense? Are there any questions with this? You guys want to do one more? All right, we'll do one more and then we'll do some different problems.
Do one more.
Yep. So we'll do MCPBA followed by phenyl magnesium bromide. I also forgot to put plus enantiomer up here. I don't want to lose my point, so I'll draw these both in. If you think you got it, give me a thumbs up too. Also add in a third step of water. Forgot about the quenching portion. How many of you guys got the epoxide? All right, so I'll go ahead and draw the epoxide, and then we'll do the next step together. So in this case, we would get a mixture of enantiomers. You could have that isopropyl group either as a wedge or a dash, doesn't really matter. And then in the next step, we've got this phenyl magnesium bromide, which if we were to draw out the full structure would look a lot like this, where we could treat it as an ionic carbon, right? Now in this case, which carbon is that negative charge on the benzene ring going to attack?
The less.
Yeah, the less substituted, because in this case it's basic. So it's going to attack here. And again, I'm going to abbreviate that as a phenyl group. So the phenyl group is going to be anti to that oxygen. In this case, the isopropyl group is going to be flipped up into that upward direction. And then last but not least, we've got our protonation of our alkoxide. This can be done with water or some sort of dilute acid. Should what be a wedge?
The isopropyl group.
No, so remember when you're doing that inversion, it's more a matter of it getting flipped into that upward direction. We are inverting the stereocenter, but you don't want to change it from a dash to a wedge. So in this case, we would end up with a mixture of enantiomers, and that would be our final product. Does that make sense? With the inversion?
Yeah, if you're inverting stereochemistry, shouldn't it become a wedge?
Well, let's take an analogous example. So let's review real quick. Where we've got something like bromine, methyl group. We'll do a hydrogen, and then a deuterium, right? Imagine we've got a nucleophile attacking. Right, it would attack from the backside, kick off the bromine, but we haven't changed any of the dashes or wedges. That upper methyl group would still be a wedge, that hydrogen would still be a straight line, and the deuterium would be a dash. We've inverted it, but we haven't changed any of our dashes or wedges. So it's still same old SN2 chemistry, just don't get caught in the idea of thinking every time you do this you need to change dashes to wedges. All right, you guys want to do a little bit of synthesis review or practice? All right, let's do a couple more practice problems. All right, this one, there's a couple different synthetic schemes. So I'll give you guys the starting material, and you can use other sources of carbon as necessary. So for this one, we're going to be making an alcohol. With a few carbons added in. So I'll give you guys a minute to work on this.
I've been useful before I did the stat plan.
Just like before, I would try to work backwards with this. And check with your neighbor to see if you guys are taking a similar route or if you see any mistakes or errors or suggestions. If you're completely stuck, you could tell them. All right, how many of you guys feel pretty good about this? At least halfway there? All right, I'll show you guys kind of the backwards route I would take, and maybe that'll help you guys get started. When I look at this, I immediately can see that we've got an alcohol, right? So I'd say, you know, it looks like maybe this could have been a ring opening of an epoxide. Maybe this used to be my epoxide, right? So let's break this up into two pieces. We're going to have the piece circled in blue as an epoxide. And then what would this need to be to add it into that epoxide?
Grignards.
Yeah, you could have a Grignard, right? So if we do this, we could say, all right, what sort of Grignard would we need to add into that blue piece in order to get this all coupled together?
Magnesium bromide.
Yeah, we just need a magnesium bromide coming off, right? So let's go ahead and do that. And I'd say, all right, on the green portion, that could be our two-piece building block. It's important to remember, too, that step 2 in this case would be protonation with some sort of water. All right, so you can actually buy this blue stuff. This is ethylene oxide. It's commercially available, so we don't even need to show how we make it. However, we can make it easily from ethylene and MCPBA, right? All right, so now let's show how we can make that green intermediate from our starting material. How can we make a Grignard reagent?
You just have like the halogen, you just dump magnesium.
Yeah, absolutely. So if we do this, right, we just take magnesium metal with an alkyl halide, and we'd say, all right, the intermediate must have been something that had bromine off of it because we're making a magnesium bromide. All right, so now we're getting pretty close, right? How can we get from our alkyne to our alkyl halide? We can't do it directly.
Then deprotonated first.
Lindlar's catalyst in H2 and then HBr with the antimony.
Okay, so if we were to throw HBr directly at the alkyne, the bromine would come off of the more substituted side of the alkyne, right? So we need to convert it to an alkene somehow. So I agree, H2 and Lindlar's might be a good approach. And if you do that, now all of a sudden you've got your alkene. And let me actually extend this arrow down. And then how can we get anti-Markovnikov halogenation?
HBr.
Yeah, peroxide and HBr. There's also another way you could go about doing this, where instead of a Grignard reagent shown in green, you can actually just deprotonate your alkyne, because we know that when you deprotonate your alkyne, you form an acetylide ion, which has a negative charge. That's also a good nucleophile. So a different route, if we wanted to, would have been to say, you know what if we just had this acetylide? That's also a really strong nucleophile that could ring open your epoxide, and then you could reduce it later. So there's a couple different routes to go about it. However, just like with our previous syntheses, try to work backwards, isolate your functional groups, and try to figure out how to make those various functional groups.
So I did the acetylide substitution.
Mhm.
Now to break that, would I need to use platinum as a catalyst when I use H2 to bring it down from a triple bond to a single bond?
So you were asking how to reduce a triple bond to a single bond. You just want to use hydrogen and some sort of catalyst
So I
like
still
palladium
need
or
catalyst?
platinum. Yeah.
Okay.
All right, so let's switch gears a little bit. They throw thiols into this chapter. I'm not entirely sure why. I think it's because it didn't have a better home. So let's spend a little bit of time discussing thiols and sulfides. Good thing with thiols is that they are really similar to alcohols. They're the sulfur analogs of alcohols. All right, so let's do a little bit of comparing and contrasting here. Let's name that alcohol, and then I'm going to put the sulfur analog and show you guys how to name that. So what do you guys think that alcohol would be named?
3-methyl-1-butane.
Yeah, if we were to number this, remember you want to number it so the longest continuous carbon chain has the alcohol coming off of it. And you want to number it so that the alcohol is coming off the lowest number, right? We've got a methyl group coming off of position 3. So if we were to name this, this would be 3-methyl, 1-butanol. And then if we look at the sulfur analog, it's really similar. However, this ol suffix, gets changed to a thiol. So this analog would be 3-methyl, 1-butane thiol. So really all you're going to be doing is changing that suffix coming off at the end. This is easy to do with relatively simple molecules, but when you get into more complicated molecules, the naming conventions change. So I'll show you guys what I mean by that. So this is for simple thiols. For complicated thiols, you have to change things. And what I mean by complex is you've got more than one functional group present instead of just the thiol. So let's take a look at a different situation. So if we look at this one, we've got both an alcohol group and a thiol group present. The alcohol actually takes priority according to IUPAC rules. So if we go ahead and number this, it would still go 1, 2, 3, 4. If we look at the substituents coming off, we've got a methyl group and then the SH group. Does anybody know what that's called when it's treated as a substituent?
Mercapto.
Yeah, mercapto. Okay, so if we were to name this, instead of calling it something thiol, we just treat it as a substituent. And so this would be 3-methyl.
What did mercapto come first now?
Oh, you're right. Holy cow. I can't do that. I have to like play the alphabet song in my head. I don't know if any of you, I'm like, QRST. So 3-mercapto, 3-methyl, 1-butanol. You want to switch to that mercapto type nomenclature anytime you've got other functional groups present. All right, so we've already seen how to make thiols, and I'll show you guys a little bit of review. let's say I want to make a thiol and I've got an alkyl halide. What reagent would I need? Somebody said it. Yeah, NaSH, NaSH. So is this going to be SN1, SN2? What sort of reaction would this be? SN2, right? Because it's a primary electrophile, it's definitely going to be SN2, not going to be any SN1. All right, the cool thing with thiols, though, is that they aren't good bases, right? You guys remember talking about that first term? Which means that really all they can do is substitution chemistry. So if you were to treat this electrophile with the same reagents, this would still do SN2 chemistry. It's not basic enough to do any E2 chemistry. So when you do this, you get inversion of stereochemistry. However, let's make a note that this isn't basic enough for E2. You can also do SN1 chemistry, and the other benefit of doing SN1 chemistry is you don't get any E1 chemistry, or at least not very much, because it's not a very good base in this case. So really it prefers to do substitution chemistry. All right, so let's take a look at a little bit of biochemistry here. And these involve disulfides. Have you guys talked about disulfides in your bio classes?
Yeah, in keratin, or the thick keratin, and in the, I believe it's microbes in their antigen binding site.
Or hair.
Or hair. Yeah, if you have curly hair, that's a result of disulfide linkages. And the cool thing is, you have an amino acid in your body that's got a bunch of thiols dangling off of it. Does anybody remember what that amino acid is?
Keratin.
Cysteine.
Yeah.
So cysteine is your amino acid that's got a bunch of thiols coming off. So if you've got a big protein that's kind of flopping around through space and you've got two cysteine portions off of different ends, they can actually link up together and form what's called a disulfide linkage or a disulfide bond. And so when you do this, you take two separate thiol strands and you link them together. Your body regulates these really tightly because this is a way of stabilizing the three-dimensional structure of proteins. So you can imagine if you're trying to, as an organism, create an enzyme, you want to really control the structure because the structure is directly related to the function of an enzyme. In a chemistry lab, we've got a few more tools we can do. When we do this reaction, we can typically do this using sodium hydroxide, water, and you can throw in some bromine for good measure. So this is aqueous alkaline bromine. Is this going to be an oxidation reaction or a reduction reaction? Oxidation. So if you were to figure out the oxidation number for sulfur, you could tell that it had a loss of electrons during this reaction. So you could use that same technique that we saw previously. So let's make a little note that this is an oxidation. In fact, you can actually do this reverse reaction if you want. However, you've got to change your reagents. And in this case, we have to use a little bit different reducing conditions than we've seen. We can't throw lithium aluminum hydride or anything like that at it. Instead, what you would use is HCl and zinc, and this would be a reduction. All right, so that's for making disulfides. We can also make just regular sulfides. So let's talk about that. Oop. All right, with sulfides just have one sulfur in between two carbon groups. These are really the analogs to ethers, right? And you can oxidize these too. Sulfur is kind of a strange element that way. However, again, you've got to use some pretty bizarre oxidative conditions. When you do an oxidation, you can actually form a sulfoxide. And if you keep on hitting this with a hammer, you can actually go all the way to a sulfone. And in order to oxidize it one step further, you just use straight straight hydrogen peroxide.
Is that how you mix sulfuric acid almost?
It's a good question. I'm actually not sure industrially how they make sulfuric acid. I would have to look that up. Alternatively, if you just want to go straight from your sulfide to your sulfone, you can just hit this with hydrogen peroxide and it will blow past the sulfoxide. Sulfoxides are really common reagents in organic chemistry. They do a lot of really cool chemistry. Does anybody know why?
It's non-polar.
Think about it this way. I'm going to redraw it down here. The resonance structure, in this case, you can pull up electron density onto that oxygen. Oxygen's really electronegative. And so its resonance structure is incredibly stable because sulfur, in this case, isn't very electronegative. It's okay having a positive charge, which means that the sulfur, in this case, can act as a really, really good electrophile. And you can actually use this for some neat chemistry. The reaction that's really common with sulfoxides is called the Swern oxidation, and it's a more gentle oxidizing technique than using chromium-based reagents. Unfortunately, it's not in our textbook, so I'll try to throw some stuff up on the website where you can read about more modern chemistry. Does that make sense? Yep.
How come in that last resonance structure we have a positive charge on sulfur, but in a lot of the other structures it's got all kinds of wacky numbers of electrons connected to it and there's no charges? Like the sulfone that's connected to a bunch.
Yeah, so sulfur is pretty bizarre in this respect. If we look at it, we're like, what happened to the octet rule?
Yeah.
The reality is with a lot of these, so if we look at specifically the sulfoxide, you can draw it in a form where it breaks the octet rule. So if we look at the sulfur over here, you'd say that's not following the octet rule, but over here, it's fine. And that's another reason why that's a major resonance structure, is because it satisfies the octet rule. So that sulfur has a lot of positive character on it. The reality is it's not as simple as we were taught in Gen Chem, where there's only one structure that you can draw. With resonance structures, oftentimes it's not a true double bond. It's actually in between a double and single bond, which kind of gets you around the octet rule. Yeah, it's a little bizarre that way.
So in this situation, we draw a positive sign on the sulfur more to signify that something came from there and up to the oxygen.
Yeah, and it's got a large partial positive character. Yep.
Does it also do to the size of sulfur?
Yeah, sulfur is very big, so it can do unusual chemistry. The more further down you go down on the periodic table, the less things follow the rules, especially when you get down into the really, really heavy atoms. They just kind of throw the octet rule out the window. Yeah, d orbitals are weird. Organic chemists get really uncomfortable with d orbitals.
Like xenon combined with fluorine.
Yeah, so xenon tetrafluoride, we were taught noble gases don't like to react. Reality is they do. In fact, how many of you guys read about the helium paper that just came out?
Wait, hold on. Hydrogen? Metallic hydrogen? Or was it a different one?
There was a helium paper where they actually showed helium bonding to sodium. And it like kind of threw everyone for a loop, where everyone's like, well, what do you mean helium's bonding to sodium? That makes no sense. The reality was, in order to get it to work, they had to pressurize it to over 100 gigapascals. So it was under incredibly bizarre conditions. Same thing with that hydrogen paper. I think for the did you guys read about the metallic hydrogen?
Yeah, it was kind of cool.
So metallic hydrogen's been theorized. This is completely unrelated to class. This is my side note. But metallic hydrogen's been theorized for a long time, since the 1940s, right? However, nobody's been able to prove that you can make it or that it actually exists. But it's been thought that a lot of stars or even large planets have centers that are made of metallic hydrogen. So Jupiter is a classic example. People think that there's metallic hydrogen in the center of Jupiter. So they've been trying to figure out whether or not you can make it and how you would make it. So they pressurized this hydrogen sample to over 600 gigapascals, I think. They basically had to reinvent their own apparatus to pressurize it. When they did it, they think they made metallic hydrogen. However, there's a lot of scientists around the world that are still highly skeptical because 600 gigapascals is insane. The cool thing with metallic hydrogen is it's been theorized that when it goes into its metallic state, it's actually semi-stable, and you can actually release the pressure and warm it up a little bit, and it will stay metallic. And it's thought to be a really excellent semiconductor or superconductor if you are able to form it. So completely unrelated, but cool chemistry has been coming out lately.
It's not the same
Also
thing
for
with
rockets,
H2S.
What's that?
It's not the same with H2S where you can make it into a superconductor by supercompression.
I'm not sure with that one. H2S is super toxic, though.
Yeah, well,
Yeah.
I mean, obviously, not. I think that's the highest temperature superconductor they have.
Yeah, maybe. I'm not sure. So at the end of the chapter, make sure that you guys add on to your flashcards that you fill out the rest of your reaction map. Make sure you bring it with you tomorrow because we're going to use it for our synthesis day. There were a bunch of reactions that were covered. A lot of them were review reactions, though. So the Williamson ether synthesis we covered in Chapter 8. Alkoxymercuration we did in Chapter 9. Reaction of ethers, it's pretty straightforward. It's similar to SN1, SN2 chemistry. The auto-oxidation section, I was going to mention this. You don't need to know that. That's generally a degradation pathway. It's not synthetically useful. You can read about it in your textbook if you want. For preparation of epoxides, you don't need to show the mechanism for the MC-PBA route. You do need to know the correct stereochemistry, though. You need to be able to predict the ring opening of your epoxide intermediates. And then with thiols and sulfides, I generally show these because they're really relevant towards biochemistry. However, the most I expect you guys to know is how to prepare thiols using SN2 chemistry. So it's good review for your biology courses, though. If you guys have any questions on the sapling, like I said, make sure you let me know sooner rather than later so I don't have a line out the door all tomorrow morning. Yep.
So you go from a sulfide to a sulfone.